All right.
All right. So do you get into the table of contents of the Light and Spectra
Yeah,
Lab?
I'm in there now. Oh boy, did it move me out of that thing? Okay, here we go. Light and Spectra, here we go. For the laboratories.
Actually, what we could do, we did that last time in one of the labs. I made my screen available so that everybody could see what I was doing. So let me go ahead and see if I can get that to work.
Okay, thank you.
Oh, well, I'd hope that you would see it too. I still don't see your name on the list.
Yeah, I see where it says, I'm sorry if I say your name wrong. I see Yoriki Lahasi.
Yeah,
then I see my phone number. And then I see Carol's name, Jesse's name, and then my name is under Jesse's.
Actually, that's Joanne.
Uh-huh.
You're Joanne?
No, I'm Nicole.
That's so weird. That's what it was. Sorry, Joanne. But I don't see your name on the list for some reason. Well, wait a minute. Maybe it's, no?
Do you see a telephone number?
Yes, I see you as a telephone number.
770 number, that's me.
Okay. I gotta quickly, gotta make a selection here. Okay, so the app sharing, that's what it's called when I share my desktop, should show now. Do you see the...
where it says, welcome to Live Wimba.
Oh, you still see that screen?
Yeah. You saying I should see something else at this point?
Well, I don't know. Does anybody else? I mean, it says on my screen now in that main window that your app share content is now being shown.
Does anybody else see that?
Yeah.
Yeah, I see it. Okay.
Maybe I should just log out and then log back in then.
Yeah, you could try to do that.
Okay. All right. What I'll do is I'll hang up and then try that and then see what happens. I'll let you hear back from me shortly.
Well, good luck.
All right. Thank you. I'll call right back.
Okay, sure. Okay, well, while we're waiting for Nicole to join us, does anybody else have a question?
I have a question about the Kepler's Law Lab.
Okay.
On question 1 of that lab, I know we're supposed to use the equation T equals D divided by V to find the time. And I figured out D, the distance, but what do we use for V, the velocity?
Okay, for V, you're using the speed of light. And that is 3 times 10 to the 5th kilometers per second, if you do the kilometers per second, or 3 times 10 to the 8 meters per second, if you go with the meters per second.
Okay, thanks.
Yeah, you should get something like 71 minutes or 4,260 seconds, I think.
Okay, I'll have to try to work it out again and see if that's what I get.
Okay.
I have a question. We have tomorrow to finish the quiz for 1 and 2 learning modules.
Let's see. That's for the 1010, right? 10:10 lecture?
Yes. Yeah, I thought it was
Okay.
tonight. And
Well, yeah, it turns out I extended it by 1 day because there was a student who had some extenuating circumstances. So yeah, you're certainly welcome to jump on board and take it tomorrow if you want to.
Hi, can you hear me now?
Yes. Welcome back, Nicole.
Oh, great. Thank you. I just realized I had to keep holding talk on here, but I see your application screening, so thanks everyone for being patient with me.
Oh, okay. Great. Yes, so let's go to the Light and Spectra Lab. Okay, and yeah, here in the table of contents, the website, yeah, try this one here, number 8, atomic emission spectra. And yeah, he has a whole bunch of spectra here. Of course, what you're seeing, the first spectrum right here is a black body spectrum. And then underneath, you have 2 absorption spectra. But yeah, here he has the emission spectra. And technically, the background should be entirely black, with just a couple of or individual lines. But I think he sort of the person who made this website put in the faint colors so that you sort of see the lines in the context of the continuous color spectrum where there would be. But yeah, I mean technically you should only see a few colored lines and on a black background. Yeah, so for question 1, let me just switch my notes here. You can pick any 6 elements. Of course, you're welcome to pick the simpler ones. And then draw, sketch in where the lines would be in those little rectangles on page 14.5. If you click on the element, that's what I just did, the hydrogen, then it also gives you the wavelength positions. So yeah, this would be 4,000, 4,100, 200, 300. So this is roughly 4,350. This fainter blue line. And this teal line here would be at 4,600, 700, 800, roughly 860, 870, so 4,870. So you could draw the lines. Well, since the little rectangle in the lab manual is shorter than the one that you see on the screen, you would just sort of try to get the proportions right and then just label the lines, with the wavelengths or with the colors.
So are you saying on 14-5, where it's the lab exercise, that we're just supposed to click on number 8, the atomic emission spectra that you're on right now, and just pick any one of those, and in those 6 boxes, wherever the line is indicated here, where I'm looking at the very first one, where it's maybe 4,100, the second one is 43 something, 4325, and just keep going down the line till we see that, then we're just supposed to put that in the first one, just put the number, the 4,000?
Well, what you do in that rectangle, you draw the vertical lines. And if you don't have color, you can just draw it with pen or pencil, and then write the wavelengths underneath. So you would draw the vertical lines in the rectangular box itself, and try to roughly space them so the purple line at 4100 and the blue line at 4350, you would sort of space a little bit closer together, and then a little bit further. So you just try to, don't have to get it exactly right, but just eyeball, the spacing. So you'd put the red line here at 6,560, at the very close to the end of the rectangular box.
Okay, I see what you're saying, and then just do those do that 5 more times until you have all 6 blocks in there. But the first one will be from 4,000 to 7,000, and just indicate the lines in there. Is what you're saying.
Yeah, the first one would then be hydrogen, because we're looking at hydrogen right now, for example, and then you would go back, and unfortunately the way iCollege works, I think I have to go back back out to the learning module, and then go back in. So yeah, you would scroll down, and yeah, you can select any 6 of the ones that are listed. Of course, hydrogen is the simplest one to draw. Well, if you go to helium or carbon or nitrogen, you don't have to, well, in terms of the numbers, just give the numbers of the brightest lines, and then maybe you can sort of sketch in roughly where the fainter lines are. So then
Okay, I appreciate that.
Yeah. Okay.
And this is one that we probably would have to go ahead and just scan and then upload into iCollege, correct?
Yeah, you can either scan and then attach the file to an iCollege email, or you can even take a digital picture with your phone camera or any other digital camera and then attach that image file as an attachment to an iCollege email. So either way is fine.
Okay, that makes sense. Thank you.
All right. Okay, and then in the second question, let's see. Let's go to. I think it might be in the lab intro. There's a link. Yeah, here's a link in the question hints to the unknown spectrum. And you're also going to see that unknown spectrum as a link once you open up the lab assessment of the Light Spectra Lab. So I've posted it here in the intro, but also in the assessment itself. So with this one here, yeah, you don't have to, if you look at the top of page 14-6, it says element number. You don't really have an element number. That is for face-to-face labs, because they have spectral tubes that they actually put into a little holder with electricity, and then there are some tubes that just have numbers that are not labeled with what kind of gas there's in, so you can just leave the element blank. And then you can write down the colors of the lines that you see. And it's okay with me if you just pick the 4 brightest lines, but if you wanted to, you could write down more than 4. So, yeah, you'd have several blue ones. But if you go with the brightest 4, then you'd have the blue, the teal, the yellow line, and the red line. And the wavelength, you would calculate the following way. There's a scale bar here, and depending on what kind of screen you have, what kind of resolution you have, the actual length in centimeters might be, it depends on your screen. Take a ruler and measure the length in centimeters of the scale bar, and then you would get, okay, this is so many centimeters. And in terms of the wavelength scale in angstroms, this bar also represents 802 angstroms. And since you're going to measure all your lines in centimeter positions from the left edge, you would want then to convert that centimeter measurement that you measure your lines with into angstrom. So your scale factor would be the 802 angstroms divided by the centimeter length that you had measured for the scale bar. That would be your conversion factor. And it would be like so many angstroms per centimeter. So
are we supposed to have?
Go ahead.
I'm sorry. For the wavelength, I see there's 6 different lines, and for the color and wavelength, 6 different lines. So when we go to that website that you just clicked on where it said unknown, and then it's going to be 6 different ones in there for us to do.
Yeah, do you see my screen right now?
Yes.
Okay. Yeah, I actually went to the link of the unknown spectrum, and do you see the 3 blue lines, and then there's a brighter teal colored line, a yellow one?
Yes.
Yeah, okay. Yeah, so you can take the 3 blue lines, so there would be a first 3, and then the teal, the yellow, and the red line. And, you measure them in centimeters, you know how far away in centimeters they are from the left edge, but then you need to convert the centimeter reading into the units of wavelength, which is angstroms.
I understand. And for each one, from the left to that first blue one, I'm going to write down blue, and then under that, I'm going to convert that from the centimeters unto the wavelength, and that's what my first wavelength will be.
Yes, and be sure that you add, after you converted your centimeter measurement from the left edge to the blue line to angstroms, that you add 4,000 angstroms to that, because the left edge doesn't start at 0, it starts at 4,000 angstroms. So it's like 4,000 angstroms plus, however many angstroms it is from the left edge to that line that you're doing.
That it converts into. Okay, 4,000 plus whatever it converts into.
Yes. Yeah, that's right.
Now you had to add that 4,000, went from that first blue line to the second blue line?
Well, the second blue line, again, you start at the left edge, so you go 4,000 plus whatever centimeter reading it is, all the way from the left edge to the second blue line. So then you skip over the line that you already did.
Right, and so when I'm going to call that second blue line light blue and the third blue line lighter blue?
Yeah, maybe something like that. I mean, if you want to, you don't have to do those 2 fainter blue lines. Then you just do the 4 brightest ones. The blue, the teal, the yellow, and the red. And then you would just keep in mind that whatever element you looked at had a couple of more lines than 4, but you were just concentrating on the 4 brightest ones. But yeah, if you want to do those 2, then you could just call it dark blue, medium blue, and light blue, I suppose.
Okay, I think I understand that part too.
Okay. And then once you have your wavelengths in angstrom, then you go and compare the wavelengths that you have to the table 1, to the elements that are listed in table 1. And depending on, since this table is from a different source than the website we're using, this table may show a different number of lines for that element than we have. But the lines that it does show, so the lines that you have, you should find pretty good matches for all, if not most, of the lines. So, pretty good meaning you should get all of the lines that you have, or most of them, to match, line in one of the columns underneath the element names. So it wouldn't be the case that you have a wavelength number and you can only match one line and the other lines are way off, then that's not the element. So if you only get one or two to match, you'd have to get most of them or all of them to match. Of course, another thing...
Okay, what I'll...
No, go ahead, I'm sorry.
That's okay, I was going to say what I'll do is, before we meet again tomorrow night, I'll probably try to make sure I have this one wrapped up so that when I'm talking about I'm matching the color blue with the wavelength, that I should be able to match blue, and if it's if it's 5,300 for my wavelength, that I should be able to find that under, or 5,800, I should be able to find that under sodium, and that's going to be what my element is?
For example, yes. Or, if you had hydrogen, then, you should come up with something close to 4,101 and 4,340 and 4,861. It could be something like, 4,010, 110, or 4,000, like 90. You'd get reasonably close. You probably won't get it exactly, but you should get within less than 100 angstrom of all of those lines.
Okay, perfect. And then that last one, number 4.
Oh, yeah, that's only the last one of the first part. Okay, once you have identified the element, then in column A, you write down your experimental wavelength that you have determined in number 2. And in column B, you write down the matching lines from the table 1 element that you have identified. And again, the number of lines, the table might have a different number of lines than you have, but you should have, excellent matches for most of them. And then in column C, you just calculate the difference. So the experimental value minus the known value. And, if that happens to be negative, you just write down the positive. That's what the vertical bars mean. So you're just interested in the positive difference between your value for the line and the known value for the line. So that difference goes into C. And then in column D, you take the difference you calculated in C and divide it by the known value from column B. So that was the line value from the table. Then once you have that, that would just be the fraction of how much off your line is, the fraction out of 100. Then column E, you multiply that fraction by 100. And that would be your percent error. And usually the percent error should come in like even less than 10%, but less than 15% at the most. This actually works pretty well.
And that sounds good. So again, I'm just gonna try that. I know once I get into it, I might have a few more questions that I could probably just email you in regards to.
Okay.
With that.
Yeah, sure. We can, you can send me your results and I can check them over, or you can ask me about the other questions in this lab or other labs, that's fine.
Okay, perfect. And did you have to, I think if you just have a few more minutes, I won't hold all your time unless anybody else has any questions. But
yeah, go ahead.
Or, I mean, we can wait till tomorrow because I know this will probably take maybe us some time to do, but then that will give us something to talk about for tomorrow's lab.
Okay, sure, that'll work. Yeah, either way, that's fine.
Okay, well, we can wait till tomorrow unless anybody else has another question about it.
Oh, yeah, wait a minute. I just switched back to the chat window, the Wimbo window, and I see a couple of postings here in the chat box. Let's see, Mardina asks, I have a question regarding question 7 in the lab. It states to use 3 times 10 to the 5 for the speed of light, but the chapter notes state to use 3 times 10 to the 8. Let's see. Okay, yeah, let me go ahead and answer that. See, that's also the Light and Spectra Lab. Let's see, question 7. Yeah, use the light. Okay, yeah, that's the 3 times 10 to the 5 kilometers per second value. So if you use that in the calculation, then the speed that you would calculate for the star that is moving away from us would be in kilometers per second. So then you would write kilometers per second as the unit for your speed. And if you write, or if you use the 3 times 10 to the 8 value, that would be meters per second. You can use that too, but then you would use the units of meters per second when you write down your answers. So
what lab are
when
you
it's fine.
talking about? I don't know what lab you're talking about.
Okay, I'm sorry. Mardina, did you just say something?
No, that was Nicole again. I didn't know what number.
Oh,
that
Nicole.
was.
Okay. Yeah, we were still talking about the Light and Spectra Lab. We were just talking about the second part, about the Doppler shift. So that's on page 14.8. Yeah, when you're comparing the spectrum of a star, actually just the hydrogen lines that is moving with respect to us, and you compare that to the hydrogen lines from the laboratory, and then they're Doppler shifted because the star is either moving towards us or away from us. And then based on how much they're shifted, you can calculate, that's at the very end of this section, you can calculate how fast the star is moving. So that would be the second part of the Light and Spectra.
Okay, I see what you're talking about on 14.8.
Yeah, you can do that within the lab manual. You don't have to go to a website to do that.
Okay. Did this thing, okay, so yeah, I just had to try to do it with this one here because I know this one seems more work than the actual lecture itself.
Yes, it does. I know. I mean, the one credit hour is really it's also for us instructors. We actually, because it's the face-to-face, it's just as much contact as the lecture, teaching the lab. And I'm telling you, online, it's actually more work to teach the lab because I'm getting many more questions, which is fine. That's my job. Yeah, in the lecture, from the lecture, I don't get nearly as many questions because you're not doing any complicated calculations in the lecture, or looking at images where you have to identify features and you've never seen these images before and you don't know what the heck you're looking at. So yeah, the lab is quite a lot of work.
Yeah, and I appreciate your time. I mean, you've definitely been great about helping. I just trying to wrap my head around it. And I know it's not your fault. It's just more so being engaged in trying to um, just do the process. So
Yeah, and
I'll definitely try.
I'm sorry, if you're not used to it, then it definitely takes. It's almost like your mind is a jungle, and you have to take a machete and hack some sort of path through it if you do it for the first time. So yeah, it's. I mean, I realize that it's really almost like learning a foreign language. So
Yeah, and what I'll do is, are you available on? You're not available on weekends like Saturday or anything like that. I could just email you or something, or I just have to wait till.
Well, I mean, I do check my email on the weekends. Um, I mean, I can't check it several times a day. I might check it either on Saturday or on Sunday. If I have enough time, I'll check it on both days. But yeah, I mean, you can certainly email me a question, like Friday or Saturday during the day, and then sometime during the weekend I'll get to it.
Yeah, that's fine. If you don't even get till Monday, I understand because the weekend is the weekend. So I'm just glad that that I see that they're due on all of them are due by the 20th. So maybe if I have any more questions, I can just reach out because this has definitely been helpful to have a visual and be able to walk through it. I still may not understand it right now, but at least have a visual of it. And then if I have more questions, I can just touch base back with you. So.
Yeah, and we're recording the session, so you could even go back and then, go through some of the things that we talked about.
Oh yeah, that's true too. Thank you. So what I'll do is I guess I can sign off now and then work with this, and then tomorrow tomorrow the same one at 8 o'clock as well?
Yes, 8 to 9, and yeah, that was in the 1020. Yes, 1020 lab. Yes, it is. So yeah, let me know if you have any questions tomorrow. Maybe to take a look at the second part with the Doppler shift. And,
Okay.
See you tomorrow.
Okay, bye-bye. Thank you.
Okay, sure. All right, does anyone else have a question?
No, I don't. This is Joanne. I'll review as well. Okay. Thank you very much.
All right, well, have a good night, and I'm glad you were able to make it.
Okay, you too. Bye-bye.
Thank you. Bye.
Hey, this is Jesse. You still there?
Yeah, I'm still there.
So I tried the speed of light on that, and I think I'm just getting lost in the math, but I'm still struggling to figure that one out.
Okay. Yeah, let me switch over to the e-board. See if I click on this. Okay. Okay, I just clicked on the e-board. Yeah, okay. Here it comes. Okay, so yeah, let me switch my pages. All right. Yeah, let me just write out the problem. Okay, so that would be okay, Kepler's laws, question 1. So you're using what formula do you use for the speed? I mean, sorry, for the time.
I used time equals distance divided by velocity.
Yes. Okay. So time equals distance divided by the, velocity or speed. Okay, so we need the distance and we need, well, we are already given the velocity. So if you go with the kilometer per second value, 3 times 10 to the 5 kilometers per second. Okay, and what do you use for the distance?
I subtracted Earth's orbital size from Mars's orbital size.
Oh, from Mars or Saturn? Because in question 1, you're supposed to use Saturn.
Yeah, I apologize. Saturn.
Yeah, no problem. Okay, so we have the Saturn, semi-major minus Earth, semi-major. So that would be 9.4554 AU minus 1 AU. Okay, so you get a value of 8.54 AU. But the speed is in kilometers per second, so we have to convert the distance of 8.54 AU into kilometers. So what kind of conversion factor were you using for that?
This is where I got lost with it.
Okay.
So
let me quickly go to the lab. I think it's in the lab hints, or the lab intro. I'm just switching over to the 1010 lab class on my desktop. Okay. Okay, yeah, I'm looking at the table of contents now, and I'm clicking on the lab intro. Yeah, I think I've posted, yeah, here it is. I just wanted to make sure. So the conversion factor is that 1 astronomical unit equals 1.5 times 10 to the 8 kilometers. So let me put that in here. Oops, I can't get back into the window. Oh, here we go. Okay. So I'm still. Okay, I don't know what's blinking. Something's blinking here. Okay. 1 AU equals 1.5 times 10 to the 8 kilometers. Okay, so then you can convert the distance. D is equal to 8.54 AU, and then you want to multiply it and the factor in such a way that you cancel out the AU and you wind up with the kilometers. So you put the kilometer value in the numerator, 1.5 times 10 to the 8 kilometers, and then put the unit that you want to cancel out, So the 1 AU, oops, beeping at me. Do this again. Oh, okay, here we go. So the 1 AU you would put into the denominator. Okay. Yeah, and then you just multiply the 8.54 times 1.5 times 10 to the 8. And you have to break out a calculator here in my applications. Okay, here it is. Okay, 8.54 times, okay, this is of course just the computer application that I'm using here, so yeah, 1.5 times 10 to the 8 would be 150,000, wait a minute, 150 million, 10 to the 6 is 1 million, so times 150, okay, and I'm getting 1.281 times 10 to the 9 kilometers. So oops, I'm typing it. What did I just say? Typing it in the wrong thing.
1.2 times 10 to the 9th, I think.
Yeah, I think that's what it was. Yeah. Okay. 1.281, I think, times 10 to the 9 kilometers. Okay. So now you have the distance in kilometers. You can take that back to the time formula and plug that value in, and then you have everything in the correct units.
I plugged in the 8.54 AU times 1.5 times 10 to the 8, and I got 1.281 to the 10th.
Yeah, maybe I just miscounted that. Let's see. Yeah, let me double check on that real quick. Hang on just a second. Don't trust my little calculator here.
All
on
right.
the computer.
I'll rework it as well on my end.
Oh, okay. All right.
So basically, we're just converting the AU into kilometers.
Kilometers. Yeah, or kilometers.
Kilometers.
Okay, no, I'm checking the official solutions, and it does say 1.28 times 10 to the 9 kilometers.
I don't know, maybe I'm putting it in my calculator wrong. Do I need to work out the 1.5 times 10 to the 8th before I multiply it by the 8.54?
It shouldn't really matter. Actually, what you could do, just multiply the 8.54 times 1.5, and then that should be times 10 to the 8. So you wouldn't even have to enter the 10 to the 8 into the calculator. You just hang it and put it at the end with the 8.54 times 1.5, whatever that result is.
Comes out to 10 to the 8. So it's 12.81 times 10 to the 8.
Yeah, okay, and then you can pull out another factor of 10 by converting the 12.81 into 1.281 times 10. And then
yes.
you get the additional factor. So that'll turn it to 10 to the 9. Okay, I'm just writing out the calculation here.
I got it. I got it now. 1.281 times 10 to the 9.
Mm-hmm.
And this is for the distance, correct?
Yes.
D, because we're given the velocity.
Mm-hmm.
So now we would divide this by the velocity, which is 3 times 10 to the...
Yes.
Which is 3 million.
You mean 3 times 10 to the 5? That's actually 300,000. Well, if you divide by 3 times 10 to the 5, make sure that you put the entire number in parentheses. Otherwise, it'll just divide by 3 and then, multiply the exponents or something like that. So 1.281 times 10 to the 9, and then divided by parenthesis open 3 times 10 to the 5, parenthesis closed.
Yeah, 4,270.
Yes, that's okay. So that's the time in seconds it takes from Saturn at opposition to get to Earth. So how would you convert that to minutes now?
Just divided by 60.
Exactly, yeah.
And you get 71 minutes.
Yes.
Just like you said earlier.
Correct.
Excellent.
All right.
Okay. All right. I know it's 9 o'clock, so I don't want to keep you tied up. I did have another question, number 6. I'm not sure what the question is. What the question is asking me.
Okay. Yeah. So that's
Go
number
ahead.
6 of the same lab?
Yes, please.
Oh, okay. Yeah, I can do that real quick. Have you been able to display Mars's orbit? See, let me switch to the app share again.
Yeah, you do that on the UGA website, correct?
Yeah, it used to be UGA, now it is actually GPC, but that's the website you're using. Okay. Okay, yeah, you should see my desktop now. So I'm going to the learning module.
Yeah, I can see your desktop.
Okay, great. Yeah, the GPC Astronomy Lab, which is item 7 on the table of contents. Yeah, and then scroll down to Kepler's laws. Okay, and then you click on, let's see, Kepler's 1 or Kepler's, I think the Kepler's 1 alternative comes in a little bit better. Yeah, and if you scroll down, you get these fields where you can enter the eccentricity and the semi-major axis based on the numbers of the table, the solar system data table. Okay, so for Mars, we have a eccentricity of 0.09 and a semi-major axis of 1.52. So I'll submit that. And so this is what Mars's orbit looks like. I know the question is a little bit confusing. I don't know if there's a better or good way of asking this. Without considering, so that's question 6, without considering the position of the sun, which should be off center, can you tell just by looking at the shape of the orbit whether it is circular? Maybe the question should have had a or not at the end. Well, if you put your finger and just block out the sun on the computer screen, would you be able to tell that it is not circular? Yeah, that's
No, it looks pretty circular to me.
Yeah, so that's sort of what you want to write down. If you don't consider the position of the sun, it looks very circular. And that's actually the reason. Yeah. Go ahead.
So with the sun being slightly shifted to the left, it basically is indicating that it's an ellipse, not a circle.
Exactly. Before Kepler, the orbits were so close to actual circles that people didn't even wonder about what the orbital shape might be. You know, with that whole Greek thing about circles being like the perfect shape and everything in the sky is, you know, perfectly spherical and circular, they just stuck with that. And Kepler was the first one to plot the orbit and the position of the sun and noticing that it's, well, wait a minute, it's a little bit off center. So maybe circles are not the best model. So yeah, that's what these two questions are, question 6 and question 7. So that's what they go on.
Okay. All right. I got that.
All right.
I believe that's everything.
Okay.
When's our next?
I'm sorry.
When's our next session for this class?
Okay, let me just switch to this schedule real quick. Okay, always have to make sure that I'm in the right class. Okay, so that's the 1010 lab. And, okay, so the next session would be Friday, February 10th from 8 to 9 p.m. again.
Okay. All right.
Okay, here it is. All right, okay. Well, if you have any questions in the meantime, just send me an email.
I will do it. Thank you so much for your time.
Oh, you're very welcome.
All right, have a good evening.
Okay, you too. Thanks.
Bye-bye.
Bye.